Okay, thank you very much. Thanks for the invitation. I'd like to start saying that this is a little bit work in progress, so I'll state some results, but hopefully there will be more. I'm working over an algebraically closed field, but the characteristic will be arbitrary. So let me recall for the senior participants that a rational resolution is the following. So proper birational map, birational morphism, that X is non-singular. So in other words, it's a resolution of singularity of Y, satisfying the conditions that OY F lower star OX is an isomorphism. The higher direct images. Oh, okay. Let me make a notational change. I'd like to call this W. I'd like to call something else Y. So hopefully, Y is actually not too hard to correct the W. So maybe. Okay, and 3, since we're in arbitrary characteristic, we also require that the canonical sheaf also has the highest cohomology. In characteristic 0, this is automatic by the Grauert-Riemenschneider vanishing theorem. Okay, so good. Now I would like to generalize this for pairs or for logarithmic varieties, if you like. So what is non-singular for pairs? Well, I think probably many people or most people know that's simple normal crossing. So we would like to look at pairs x dx, where x is a non-singular variety and dx is a simple normal crossing divisor. So that means that the dx is an integral divisor reduced, and the components of dx are non-singular, and they intersect transversally as much as possible. So locally, they look like the coordinate hyperplanes in affine space. Okay. So first of all, let's see what happens in characteristic 0. For possible generalization. So, is there a Grauert-Riemenschneider vanishing for pairs? So, what would be the equivalent of this for pairs? Well, instead of the canonical sheaf, we would look at the log canonical sheaf. So, one would like to have a vanishing theorem like this. But this is not true like that. And a very simple example is blow up the intersection of two lines in a surface, in a smooth surface. So let's say, this is W, dW is X, dx. Oh, right. I told you Okay, I'll get back to that later. So let's say dx is these two lines, so it's just the strict transform of those two lines.
Why the strict transform?
I'm sorry?
Why the strict transform?
Why do I do strict transform? You have to do one or the other. So one reason is that I would not like to have exceptional divisors as a component. Another is that, so are you thinking the preimage?
In the smooth case, you don't add the exception.
Janner says, in the smooth case, you don't add the exceptional divisor. But I have a better, or I have different reasons. So, if you're thinking to take the pullback, then you didn't do anything. Then the projection formula says that, so if this dx is the pullback of the dw, then this would be just that twisted with dw, right? Of course, we could do that, but then I'm done and we can go to lunch. So I guess you could say, let's take the preimage and take the reduced divisor. There is actually, sure Carl is here.
Yeah.
Yeah, so Carl has a theorem that does something about that. But that leads, yeah, this leads to a different thought. Okay? So let me, if this was not convincing enough, then let me claim artistic freedom. So that's what I choose to do. Okay, but in this case, let's say, so I'm claiming that for this map, this is not true. Oh, okay. It's actually easier to, you will also want the dual version of this. And let me actually demonstrate that this fails. It's slightly easier because you just look at OX mapping to ODX. And let's say this point is O, these 2 points are P and Q. So if you look at this thought at O, then this thought at O, this is just OW at O. And the start of this guy at the point O is really the direct sum of dx at Q and dx at P. So you can see that, I'm not sure how to denote this, but this is not surjective. Okay? So the following map is now 0, and the following guy here is OX minus dx. Okay. So this will fail, which is okay. So this will not be true for all birational morphisms, but in some sense, here we actually didn't really need to do this. This was already SNC. So this is sort of extraneous. Don't want to do that. Okay, so I guess I haven't defined what a resolution is. So let's say that now if I have a map, so these are both pairs, but this is not necessarily SNC. So I require that, so this means a map from X to W, which is a proper birational map. I would like this pair to be an SNC pair. So by an SNC pair, I mean these two things, and such that dx is the proper transform of BW. Okay, and we postpone arguing about whether that's a good choice or not. Okay, so there's still the question if there's a logarithmic version of Grauert-Riemenschneider vanishing, and there is, but we need to assume something. So for that, let me introduce the strata of a simple non-recursive divisor. It's just all the possible intersections of the components. So where dx is the sum J1 to R, and this index set is a subset of all the indices.
So you don't take connected components of these intersections?
Yes, thank you. Corrected components of these. Okay. And now, if in addition to this, or to these, we require that for every stratum, the restriction of F to T is generically finite, then Ri at powers are omega x dx is 0 for every positive alpha. And from this example, you can actually see that this is basically necessary. Okay? Yes. So if this dx is a Cartier divisor, which in this case it is automatically since x is smooth, then these two things are equivalent by duality. Okay? So
So this is an assumption on a resolution.
I'm sorry? No. So this is a condition. So if this holds, and so I should probably do this. So these are the conditions. And that's the.
So you're saying that the thing above is not a resolution?
Here? Well, this fails.
So why don't the conditions on strata satisfied?
You're saying that it's not satisfied and therefore it's not a resolution.
Are you defining something?
I mean, isn't in your example, isn't F restricted to each strata upstairs?
Yeah, but upstairs is OX, downstairs is omega x.
Yeah, okay. That wasn't the best example, I guess.
No, but
So what?
why does the implication for?
That's the theorem. I'm not claiming I proved it.
This question means why is this example
Because that's OX and downstairs equals omega.
Yeah, I'm lying somewhere here.
Peter, where you lying?
So are you declaring that the map upstairs is not a resolution because it doesn't satisfy the condition downstairs?
I shouldn't claim that because it looks like it satisfies that. Okay, so In this example, this will hold, which puts into doubt my claim that these two are equivalent.
So even for d equals 0, they are not equivalent. Yeah?
That's right, yes.
That's right. So let's forget about equivalence.
Yeah, but for d equals 0, they are equivalent if the target is cohomological. And here the target is cohomological, so it's something fishy.
No, that's for cohomological. It's rational. One defines rational, the other is cohomological. Just Grauert-Riemenschneider. This is not equivalent.
Okay, you're right. Okay.
Could you repeat that? We did not hear what Janusz said.
Janusz just pointed out the obvious. Which was not obvious to me. So we need him. We need the voice from below. If you forget about dx here, the second condition in characteristic 0 defines rational singularities. First condition is automatic, so they can't be equivalent unless the target has rational singularity. Okay? Yeah. I shouldn't have said that they were equivalent. I tried to cut some code, so okay.
So what are you saying in that box?
In this box, so I'm only claiming this for omega.
And only claiming it under what assumption?
These assumptions. So this statement is still okay.
Okay. So what?
This is not a counterexample to that. It's a counterexample to this one.
You're saying this is the analog of Grauert-Riemenschneider.
Isn't it? I mean, without this, that would be the analog that you would expect. And I claim that if you don't assume this, in fact, I think, let me have tried to make up an example at the board, so I'm pretty sure I'll get it. Okay? But
Ending the vertical line.
I was gonna say that, but I was afraid. So Janusz says add the vertical line as Dan suggested. And yeah, I'm pushing every blame to others. Then this would fail. But it would certainly fail this condition, which doesn't mean that it necessarily fails that one, as we know. It's not in green characters world. Anyway, I stand by this statement that this view is okay, and I claim that it's not always. And it's not always, not always true without this condition.
But what's the view on the side?
Is it Kovács theorem?
It's a very easy concept as a Grauert-Riemenschneider. It's right on the obvious example.
Yeah. Okay, so basically the proof is that you take one component of dx, write down the logarithmic or the adjunction sequence for that, and then use induction. And this condition tells you that you can keep using Grauert-Riemenschneider because so in each step, as you restrict, it will still be a birational morphism. That's yeah. Okay. So yes. We got to my second page. Not get very far. So in the v equals 0 case, we have the theorem that if W admits rational resolutions, then all resolutions are rational. And in characteristic 0, in the previous talk, I showed those who were here that this has a very simple proof in characteristic 0, assuming resolution of singularities, and that so we can cover any two resolutions with a third, and the fact that we know that between two smooth varieties of proper birational morphism is a rational resolution. But in characteristic P, we can do this, and accordingly, in characteristic P, this was not known until a few years ago. So this was proved by Chatzistamatiou and Rülling. It appeared in 2011. They published the preprint in 2009. So this not an easy.
Can you read what the theorem says?
What the theorem says?
Yes.
Oh, this. If W admits a rational resolution, then all resolutions are rational. So, so what it says is that if you have a rational resolution, then any other resolution is also rational. Actually, what they prove is more. They do not assume that this is necessarily a resolution, just that x and y are non-singular and properly birational. That is, that there's a z and proper birational maps here, but these don't have to be birational. Then they prove that the push forward from x to w or from y to w are
Push forward of O?
Push forward of both O and omega, little omega. Okay? Hopefully I'll get back to this in the logarithmic case. And I'll just say what the result is. Okay? In fact, let me try to set this up on how we would go about this in the logarithmic case. So let's say I have two pairs. Now, in the setup, I don't want to make W a logarithmic pair. So this is actually, we're thinking of this as a base scheme. So these are W schemes, and so are dx and dy. And we assume that these are SNC pairs. And then there are proper birational morphisms here. So pi and sigma are proper and birational. But if we want to make this work in characteristic P, then we do not want to assume that G is non-singular. So in characteristic 0, we could assume that, but in characteristic P, we don't.
Are you requiring anything about dx and dy relation?
Yes, in a second. So that's actually that's part of the issue that.
What was the question?
Oh, sorry. If there's some relation between dx and dy, there is. So what we would like to do is look at the push forward of omega x dx. So, okay, I would like to do both of these cases, but they're slightly different. So I'll just talk about omega, and that's why my ill-conceived comment was made that I wanted to get rid of the other case. It has to be slightly changed to deal with that. But what I would like, so this is the goal that we'd like to make an assumption on how these pairs are related, so that we get this. And so what Chatzistamatiou and Rülling proved was actually that in this case, Ri f lower star omega x are isomorphic to Ri g lower star omega y, and the same for Ox and Oy. And so even in the d equals 0 case, I'm claiming something more. I'm claiming that actually the complexes, the full derived images are isomorphic. So in their case, they just prove that the cohomology sheaves are isomorphic. Okay. Okay, so I guess I can tell you the condition that I will require of the dx and dy, and it's that I want that the birational morphism that I get from z pairs up this strata of dx and dy. Then, so they have the same number of components, and then all the strata or map that there's a dictionary between them. Okay? And that will be the condition. And so here's the idea. So actually, most of the basic structure of the proof follows Chatzistamatiou's and Rülling's proof.
The proof of what?
I'm sorry, I didn't hear.
You mean the proof of that formula?
No,
Below.
the proof of this formula. I haven't told you anything about that yet.
But you said something that the structure of the proof of what?
Oh, yes. Okay, I'm sorry. I now understand. Yes. So my proof of this formula will follow the idea of their proof of that formula, with some, obviously some changes and some additions. But I just wanted to say I'm not claiming originality for all that's following. So the main idea is this, that so we have the z, and first of all, I can replace z with something that's contained in x plus y, because obviously if z maps to x and z maps to y, then z maps to x plus y, and then I can just look at the image, and that will still have the same property. And since I didn't assume anything about the singularities of z, I can just replace it with that. And then this looks like something classical. So this is a correspondence between x and y. And in fact, assuming that these are birational, it means that z actually has the same dimension in x and y, and then the projections are birational. So it is really a correspondence. So it looks like the graph of a birational morphism, a birational map between x and y. And the idea is that we want to use that to define maps on the cohomology, so on these guys. So we use the z. Let me actually use just this page. So we're going to use the z to define maps going both ways, and then want to use the fact that this is birational to prove that those are actually isomorphism. What we actually do at the end is to look at the composition of these two and prove that that's the identity. Okay? And how does this happen? Well, the z is in here, so there's naturally a class of Z in the Cho group of X cross Y. And this actually, you can write down how this induces a map on the Cho groups. So if you take an element here, and let's say that, let me upgrade this pi and sigma to be the projections from x, y. So, I'm sorry, x cross y. So pi will denote the projection from x cross y to x, and sigma the projection from x cross y to y. So I map this to, so first of all, I pull back alpha to the product, then hop it with the class of Z, and then push that down to Y. And this, for a class in the Cho group, gives me a class in the Cho group of Y. Okay? And we'd like to do something like that for these. Now, I will actually restrict to this case. It's a little bit easier, but at the end, I'll try to say a few words about how to do the complex case. By complex, I don't mean C, I mean complex like that. Okay, so actually, a very useful trick that they introduce is that in order to do this, we actually have to look at the cohomology of all the exterior powers of capital omega. And if you think about this and you think that, okay, I would like to do something like this for cohomology like this, then it's not an unnatural thought because the Z is in the middle cohomology. So if you look at the fundamental class of Z that's in some kind of a cohomology related to this guy, it actually ends up in the, let's say if X has dimension D, it ends up in the HD of omega D of the product. And that's somewhere in between these. Okay? So if we want to use this to relate to that, then we actually have to deal with all the exterior parts. So that leads us to consider logarithmic Kovács cohomology. This has a...
It's simplifying the graph of the rational graph with the next one.
Yes, essentially. So, in theory, I just had a Z that mapped to both, but then you can map it to X plus Y. And so replace the mean to that. Okay, so we have X dx is a simple crossing pair, and then we define X dx to the X sum of these groups. Okay? And so I'm working on this omega version. If we want to do the OY minus dx, then we have to add minus dx here. So it's not just log, but a minus dx. And it all fits together well, because if you look at duality, then this minus d. So if you want to do duality for logarithmic forms, then in the dual version you have to add a minus d. And also, if you look at Hart's theory, and let's say x is not necessarily proper, then this logarithmic Hodge decomposition gives you the singular cohomology. So if I don't have this, and I just get the singular cohomology of the component of D. If I add this, I get the compactly supported cohomology. And the pointary duality, those are the ones that do. So it all fits together.
So what's the upshot? When do you use the minus D?
Okay, so I'm just working on the omega, and a similar but somewhat different proof works for the O minus D. And for that, I need to do the minus D. But, so if Q is 0, then this is just O. So this will not be the O minus D. But if I put a minus D here, then it will be D. But then, so in that case, the top guy is actually just omega. So it's sort of, that's actually, which will not be apparent from this lecture, but that's the main difficulty in this whole proof, that this addition of D kind of makes it unbalanced. So as long as you don't have a D, everything is very symmetric and it's sort of, you can do things together. In this case, very often you have to work with this or the minus D, even in this case. Because some of these maps are defined using rotating duality. And in that case, you actually have to work with the minus D. So it's just, it's kind of a balancing game to keep everything intact. Okay. I have until noon. Okay. Okay. So I have this, and then of course we have the non-log Hodge cohomology, which is just the same thing with the x0. And then this guy is naturally a subsheaf of that. So we have a natural map from the Hodge cohomology to the log Hodge cohomology. And on the other hand, for the choke cohomology, we have a class map. So there's a map from the choke cohomology to the Hodge cohomology, and this is just, I think Rotendi called this the fundamental class, maybe. So the map is that if you take an irreducible subvariety of X, then it maps to an element, okay, irreducible of codimension P, then it maps to an element in HP omega P, and then via this natural map, we can actually think of this as a map in here. And actually, if you want, you could even introduce yet a third cohomology theory that would be the pure Hodge cohomology that would have P and Q equal, and then this map actually factors through that, so we have a whole series of these. Okay, so now the idea is that this Z introduces a map on the cohomology, on the child groups, and then we have a map from the child groups to our log cohomology, log Hodge cohomology, and then the idea is that we would like to propagate this map to the Hodge cohomology. So what it needs is defining pullbacks and push forwards for these cohomology theories, And that's something that I will sweep under the rug for now. I'm happy to discuss this with anyone. The pullback is somewhat, it's not surprising. It's essentially the pullback. The push forward goes through logarithmic duality. So if you're familiar with Chatzistamatiou and Rülling's paper, it's essentially the same thing. But as I mentioned, and yeah, it was up here, there's this game to play with when you look at log and minus d, and keep everything balanced. So it's sort of checking a lot of, figuring out how certain maps go and checking lots of compatibility. And what I claim is that, okay, I didn't write it down, but I said that the condition is that there's this one-to-one correspondence between the strata. If that holds, then this can be done. That this pullback and push forward works, and it's compatible with this fundamental class. So what we end up with is we have this z in x plus y, and that induces maps between the logarithmic Hodge cohomology of x and the logarithmic Hodge cohomology of y. And now, yet another observation from Chatzistamatiou and Rülling, which is sort of, you could say, this is probably the heart of the entire proof, both theirs and mine. This is the following, that if you have a class in x plus y, where p is the dimension of x and dimension of y. So I'm thinking that we're in that situation that x and y are birational. And assume that so pi is the surjection to x and sigma is the surjection to y. So assume that pi lower star of the support of alpha has codimension R in X. Not claiming this is true for Z, so I'll show you what this is applied to. But if this has codimension, I mean, of course it is true for Z because I can choose R to be anything. But the interesting thing will not be applied to Z. So if this has codimension R, then this induced map that we have here, then the restriction of the map induced by alpha, and I probably should have written here that this is not just for Z, but for any show class, there's an inducement. It's just the same way. So, restriction of the map induced by alpha from hx dx to hy dy is 0 on a part of this, 0 on the dx sum, where q is at least v minus r plus 1 and at least p. So for hp x omega x q log dx. Well, in their statement there was no log, but it's essentially the same thing. And notice the following. This means that if R, okay, I should say corollary, if R is positive, then, and Q is the dimension, then this is all there is. Right? So if Q is equal to D, and R is at least 1, then this includes everything. So what this says is that if I have a Chow flux that subjects to X and does not cover X, then it does not affect what happens with this guy. Does this make sense? Oh yes, right. Then I'll have this. So actually, going from cohomology to sheaves is just the usual way how you actually can exhibit this as cohomology. Then we take an open set and then take the preimage and do everything locally and prove that they actually group together to a sheaf. So it's a relatively easy reduction, and that's why, for example, I didn't want W to be a pair. It's just a base scheme. That the isomorphism is reduced to the case when W is actually the base scheme. And then this R is just cohomology. You're right, I skipped this. So, I'd like this statement to get through because this is important. So the statement is that if you have a correspondence that maps to just a proper subset of X, then that does not affect, that its effect on the cohomology of omega is nothing. They cannot affect that map. And I think, I don't know, okay, I see that. So how does this prove what we want? Erase this. So the way this is applied is the following. So still in the Chow case, we can define composition of correspondences. So if you have 3 of these guys, let's say X, Y, and well, they're not used yet. Okay, V. So if I have a correspondence here, and the correspondence here, then I can define the composition of them. Okay? Let me not get into that. It's, you've probably seen this. It's not new. So you can define the composition, and you end up with, so I guess this would be something like this composed with that is in Chow of the outside guys. And now what we do is, so Z sits in X cross Y, and the transpose of that sits in Y cross X. So now if I compose Z transpose with Z, this gives me the class in X cross X, and then what one proves is that, well, this will contain the diagonal of x plus some guy that we prove that the projection of this to the first factor that does not cover x. And that's, I think you can guess how the proof goes. There's an open set where this is an isomorphism, so this guy cannot land there, so it lands in the complement. So this E1 will play the role of alpha. So, well, we need to see, so there's a lot of background that I'm not, background checking that I'm not telling you, but you want to say that the morphism induced by this class is just the sum of the morphisms induced by the individual ones. But this lemma tells me that this E1 doesn't affect what's happening on the homology of omega. So when I compose Z and the transpose of Z, which is essentially the inverse, then the effect on the homology of omega x is just the same as the diagonal, which is the identity. And then you do the same with the opposite one on y. So what you get is that you have two maps, and this is the identity, and this is the identity. So individually they have to be identity. So that's essentially it. And I promised I'd say a word about how to build the complexes. And it's basically the exact same setup, except that instead of cohomology, in this cohomology theory, we deal with the complexes. So instead of mapping to the category of graded abelian groups, we map to the derived category of coherent sheaves on X. And you have to lift this class to there. But that's actually possible because this is done using the causing complex. Is that how you pronounce that?
Yeah.
The same thing. And that's a complex. So usually this is written down by applying cohomology to the complex. But you can actually do the same thing and stop at the complex level. And that's how it's done. And I'm done.
Thank you very much. Are there more questions? Yes.
So is X and Y projective in your situation?
You mean over W?
No, just in itself.
Okay, what is projective?
X and Y. In that diagram. Yeah.
Right, so that's why I asked, you meant over W, right?
Yeah, over that.
So, okay, I kind of didn't touch that point. What I said here would require that. Actually, you don't need it. So, and this is again due to that. What they do is they deal with cohomology with support. So there's some additional data of a collection of supports, and what you require is that this map on the supports is proper. What this is actually good for is that this allows taking open sets and then restricting to that and doing it there. So it's actually, the answer is no. When you do this, then you actually have to take cohomology with supports. Does this answer your question? But the simpler thing would be to say, yes, let's assume that it's projective.
Any other questions?
So recently they gave a much simpler proof of their result.
Well, what they gave, right. So they gave a much simpler proof and more
Yes.
wide, but not of this, but the vanishing. So they proved that essentially that if you have a morphism between non-singular or actually regular axon schemes, then it's a rational resolution. So what's your question?
They have a logarithmic version that's like the mixed characters.
I don't know. Maybe. So my proof doesn't do that, and so they also don't prove this. So I was concentrating on. So they don't prove that if you have two, then they are isomorphic. What they prove is that if you have one map that's proper and birational, then the higher directivities vanish. And here, this doesn't require this to be birational or proper. But certainly, it's a good question. But obviously, you would have to limit the kind of maps you allow. But even for that, I don't know.
Other questions? Let's thank the speaker again.